All right. Hi, everyone. Hello. So today I want to do several things. We're going to come back to our interview puzzles, and we'll have a new one, and we'll then do nested loops. So nested loops are just loops within loops. I also had some pictures to show you, actually. So last time we spoke about kind of lather, rinse, repeat as infinite loops. I think so the joke again, so I think those are like unusual words in English. So I know. So lather means like put kind of the soap on your hair, and then rinse means kind of rinse it with water, repeat. Yes. So that's kind of the classic joke. I know it's not that funny. So I wanted to point out, so I did go to Shoppers the one time and looked at all the shampoo bottles to see if it's true. And well, at least like right now, it's not true. So this would be like the typical thing that you would see on an actual shampoo bottle if you read it. It says like lather, rinse well, repeat if desired. So the while loop there was like while desired, lather and rinse. Okay. So that issue has been fixed. So that's supposed to be like what the old style shampoo bottle would look like, but this is of course like a fake, not even like an AI fake, just like a Photoshop kind of thing. It's not a real shampoo bottle. So there's like jokes about people like putting stuff in shampoo instructions because nobody actually reads them. So this is like one of the ones that they found in Google Images. So this is a pet shampoo. So like remember to eliminate all escape routes well in advance for the pet. Once your pet is slippery, he or she is suddenly smarter and faster than you are. That accords with my experience of trying to bathe a dog. So yeah. Okay. Anyways, so that's that. So I want to first go back to the interview puzzle that we had a while back, and that was compute efficiently the number of trailing zeros in n factorial, right? And if you remember, like the inefficient way was, well, first you compute n factorial, and then you try to figure out how many zeros are at the end of the number. How do you figure that out? Well, you try to divide by 10 as many times as possible until you get to the point where you cannot divide by 10. And the number of times that you divide it, well, that's the number of zeros, right? So if you try to divide this kind of number by whatever, 10 5 times. So the first time is going to be this, second time is going to be this, third time this, fourth times this. So as many times as you eliminated the zero, as many times as you divided by 10, that is the number of zeros. All right. So the reason it's inefficient to do it that way, so to first compute n factorial and to then try to divide by 10 a lot of times, is one, it's very expensive to compute n factorial for a large n because it's a huge number. So just writing it down becomes difficult. Two, dividing by 10 repeatedly is maybe not the best thing you can do. So here's the idea for how to do it. So what's n factorial? Well, n factorial is 1 times 2 times 3 times 4 and so on times n. What's the number of zeros at the end of a number? Well, that's the number of factors of 10 that are in this number, right? So this would be 10 times 10 and so on times 10, some number of times some other stuff, right? So basically what I'm claiming is you can factor n factorial. And the question is, well, how many factors of 10 are there? That's how many trailing zeros there are. Because each factor of 10, that's another trailing zero. So how do we figure that one out? Well, what's a factor of 10? Well, 10 is 2 times 5. Right? So we can rewrite it as 2 times 5 times 2 times 5 and so on times 2 times 5 times some other stuff that's not relevant to factors of 10. Now, in fact, if you look at this, what's important here is the factor of 5. And that's because there's lots of factors of 2 going around, right? So you multiply by 2, then you multiply by 4, then you multiply by 6, then you multiply by 8. Every time you do that, that's at least one factor of 2. You multiply by 8, that's 3 factors of 2. So really, what you care about is how many factors of 5 there are, because there's always going to be 2's in order to complete it to a 10. That's not the problem. The problem is how many factors of 5. So, okay. So this is 5 to the k times whatever, including the 2's. So we factored out the 2's. So the question we want to answer is, what is k? So can someone give me a wrong answer to what is k? That still is kind of right. Like, what's the first thing that you think of that's wrong? Yeah. Well, but you don't know that, right? So you have a number like m is equal to n factorial, and I'm asking how many factors of 5 are there? Yeah. It's not negative. Not negative. Well, give me a concrete guess. You can't, like, there's not a formula. No, it's not exactly the number of digits. Yes.
Number of 10 so 5 plus the number of 5.
Well, sure, but you don't know what that number is. Like, you might as well say, well, k is just the number of 5s and then factorial. What's your problem? That's the answer. So, okay, yeah. Yeah, that's the wrong answer I was looking for. Thank you. So, no, like that. Thank you. That I think that's exactly what you meant, right? So the idea is, well, like, what's the number of factors of 5? Well, every 5th element supposedly would be a factor of 5 at least. It's a lower bound than the answer. It's not exactly the answer, but that's kind of it, because, you know, like 5 contributes 1 factor, and then 10 contributes 1 factor, and then 15 contributes 1 factor, and then 20 contributes 1 factor. And then, well, you get to 25 and you find that, well, actually 25 is 5 times 5, so that contributes 2 factors. Right? But kind of as a first guess, it's not a bad guess. So just n divided by 5, that's kind of at least the number of factors of 5 and n, because 5 gives 1, 10 gives 1, 15 gives 1, 25 gives 1, and so on. Make sense? So, all right. So then, what do we do now? So now our question is, okay, the series looks kind of like this. So we have 5 to the 1 times, well, I should say something like this. So you have n divided by 5, and that's the number of 5s. So the issue is every 5th contribution actually gives you 2 factors of 5, right? So what you can say is, well, I'll add for 25 and for 50 and for 75 and for 100, I'll add 1 more. So how much would that be? Well, it's every 5th of the n over 5. So that would be n over 5 over 5. Right? And then every fifth of those also contributes 1. So that would be this much, again, over 5. Is that making sense to people? So here we just counted like 1 factor for 5, for 10, for 15, for 20, 25, and so on. And I said, oh, but for 25 and for 50 and for 75 and for 100 and so on, there's 2 factors of 5. And I said, oh, for 125, it's actually 3. And so on, right? So this is accounting for just the basic kind of every fifth number from 1 to n. And then this is every fifth number of the ones that are divisible by 5. And then this is every fifth, this is just 5. And then every fifth of those, and so on. When do you stop this? Well, when this becomes 0. Right? So if you are not counting up to 625, so 635 is 5 to the 4. If n is smaller than 625, you don't care about the fact that every 625 you contribute 4 factors of 5 because never get. Right? So let's compute this. So we'll say, okay, so the answer is n divided by 5 plus this divided by 5 again, and so on. So we'll say result is initially n divided by 5. And then we'll keep going. So we'll keep dividing by 5 and adding to result while there is something to add. So we'll say while n divided by 5, current is also going to be n divided by 5. And we'll say, let's do it nicely. So we'll say result is 0, current is n divided by 5. And we'll add current to result. And then we'll say, while the current thing that we're adding is still not 0, we'll keep going. So while current is greater than 0, it's going to be current divided equals 5. Result plus equals current. Return result. Right? So initially current will be this. And then we'll say current is this, and we'll add it to result. And then current will be this, and we'll add it to result. And then current will be this again, and we add it to result, and so on, until this becomes so small that it's 0 anyway, and then we might as well stop the loop. Make sense? Questions? All right, so like I'll do it kind of one. I'm running out of battery for some reason. So, oh, that's the reason. So, yeah, so I bought a laptop with a GPU because I wanted to like debug neural networks on my laptop. I did not consider the fact that I don't only now need to lug around the GPU, I also need to lug around the power supply that works with the GPU. So, okay. Do not repeat my mistakes. Use cloud. So, although I will share with you that I got an email today that made me smile. I bought a server with a GPU for $4,000 of your money. Thank you very much. And so now I have, well, you have it, I don't have it, but I happen to have the password and you don't. So okay. Anyway, I'll stop teasing. So okay. So from the top, what we're trying to do is we're trying to compute the number of factors of 5 in this kind of product. And the initial idea was we'll just count the 5, the 10, the 15, and so on. There's n over 5 of those. And then we said, well, like every 25, we want to count 2 5s. So we'll just add in n divided by 5 divided by 5 in order to account for the 2 5s in 25 and 50 and 75 and so on. And then the same thing for 3 5 and 125 and 625 and 5 times 625, which I don't know off the top of my head, but Python could probably help me. This much. This is, yes. And so on, right? So got it out of my head. I try to, so kind of, especially in the beginning, you want to try to like put as much on paper as possible. And then, okay, we have the concept. We just need to compute this thing. We don't care what it is for now. How to compute this thing? Well, what we'll do is we'll first compute this, then we'll compute this by dividing the previous term by 5, then we'll compute this by dividing the previous term by 5, and so on. How do we compute the sum? Well, I keep just adding current to result over here and over here inside the loop. So that's the concept. Not an easy problem, but I think a fun one. So, okay. Next interview challenge question. So a list contains all the integers 1, 2, 3, and so on up to n, except for k in some order. Find k efficiently. Right, so the idea would be if it's like 5, 3, 1, 4, then the missing k is 2. Right, so that's the concept. So I first want to do it inefficiently, and then I'll let you think about it, of how to do it efficiently. So this is this. So, okay, I'll do it like in the silliest way possible. I'll just guess and check. So I'll say, is it 1? Is it 2? Is it 3? Is it 4? And so on up until n. So the only problem is I need to figure out n because I get an L, but I don't get an n. But I can do that, of course, because what's length of L if L contains 1 up to n except for one element? Anyone? Yeah.
L minus 1.
Well, n minus 1. Length of L is not length of L minus 1. But yeah, n minus 1. Does that make sense? So why n minus 1? Well, because if it contained all of them, the length obviously would be n. It's missing 1, so it's n minus 1. Right? So that means that n is what? Length of L is n minus 1. N is... We're not moving until you tell me, not you, you know. Someone else. So length of L is n minus 1. What is n? That's not difficult. Yes. Correct. Length of L plus 1. So why is that? Well, I mean, if length of L is n minus 1, you can think about algebraically. Also, it's like you're given some number of elements and you know it's 1 up to n with 1 missing. Well, it has to be that the number of elements plus 1 is n. Because then if you add the missing element, you have n. So it's length of L plus 1. So, okay. So what I'll do now is I'll just say, okay, try every possible guess about the answer. So I'll say 4K in range. So what's every possible guess? So the problem statement is L contains 1 through n. So the first possible guess is 1. And then the last possible guess is n. So it's range n plus 1. So that's because I go up to but not including n plus 1. So I try every possible one from 1 to n. You might argue that if the missing one is n, that means that I'm given just like, for example, 1, 2, 3, and the missing one is 4. You can count or not count it as a valid case, but either way. So, okay. And then I'll just say if K is not an L, that's my answer. Right, so K is 1, then 2, then 3, and so on. And every time I check, is it an L? If it's not an L, well, I found my missing K. So here, this should give you a little bit of anxiety because you're only returning inside a conditional. So that means that if K was never not an L, then you never return anything. So by default, the function would return none. Now, in this case, it's not even specified what you should return in case none of the guesses work because, according to the rules, length L should contain 1 through n with 1 missing. If that's the case, you'll always return something. If it's something weird, like L is like all floats and there's no integers there at all, or even if it's like 1,000,000, 1,000,000,000, whatever, the problem doesn't say what you're supposed to do, so you might as well return none. It's fine. This is not an infinite loop in any situation because this just repeats 1 through n. It's just that it might be that you get to line 47 and you just return none. So if you remember, the function by default returns none. So it's as if you had said return none at the end, which you never should do because like at the end, usually you should kind of put it that way. If you're writing an actual function that goes into production, there shouldn't be situations like that where it's kind of ambiguous. Like if there is an input and if it's valid in the sense that it's all integers, you should probably check that the integers conform to the condition. But here we're writing a toy example, so we're just ignoring it. So it's fine. This should give you a little bit of anxiety, but it's fine. Now, the problem with this is not immediately apparent. Like, why not just do this? Well, the reason is, how would Python compute K not an L? Well, it has to look through the entire list L in order to find, like, is the first element equal to K, is the second element equal to K, and so on. So that means that Python must look, in order to execute line 45, it must look through every element of the list. And it does it for every guess. So it's kind of inefficient because you're going through the list and then you're going through the list once, twice, thrice, and so on, n times. So that's a lot. So there is a way to solve the missing K problem with what's called one pass over the list. So look at each element just the once. It requires like a clever trick. So whether you can come up with it or not, well, maybe it depends how lucky you get. But and depends like if you saw similar problems before, I suppose as well, that you can give it a shot. All right. Okay. Is Discord saying anything interesting? I hope it's not saying the lecture is not recorded. Okay, yeah, that's actually, I guess, from a while ago. So please ask those kind of. Yeah, that is correct. So I have not set the autograder up yet. I'm sorry. So I had like a conference thing. So yeah, please ask those kind of questions on Piazza because I don't usually, well, sometimes I check the Discord, but sometimes not. Piazza definitely gets to me, so please do that. All right, I think there is a question in the chat. How hard will the midterm be? Is the question in the chat. Medium. So, okay. Like medium, rare, you know. So, okay, yes. Thank you, but let's have other people kind of thing. But yes, you're right. All right, okay. Cool. All right, okay. Is there anything here? Serving on chestnut. Okay. All right. So, but yes, that was good. Okay. All right. So the next thing I want to do is what's called nested loops. I give you the name. I think it kind of gives people like the sense that this is something different from what we've been doing before. It's really not. With that said, people do use this expression. So nested means in this context, a thing that's within its own thing, something like that. So here's an example. So I can say for I in range 1 through 5, 6, okay? Then I'll say for j in range 1, 3. And I'll just print whatever I is I and j is j. And that is what I'll get. So here's what's happening here. What I'm saying is for I in range 1 through 6, do this block. This block happens to be a loop itself, right? So, and that's exactly what you're seeing. So you're seeing that I'm saying for I in range 1 through 6, so I initially is 1. And then when I is 1, j goes from 1 and then to 2. So that is this part of the output. So I is constant, I is not changing, it's 1. And we're running what's called, so sometimes we say the inner loop. So the loop that's within the loop. What does the inner loop do? Well, j goes from 1 and then to 2. And that's exactly what we see. I is fixed and j changes. And then this loop is done. So I becomes 2. When I becomes 2, again, I is fixed. So inside here, okay, I is now 2, and j goes 1, 2. Then it's done. I becomes 3. J again goes from 1 to 2. Right? So that's kind of the classic idea of a nested loop. So why would you want this? So one reason that you would want this is if you want to enumerate, so list all the possible combinations of the possible i's and the possible j's, right? So here's an example. Let's say that you want to try to break into a computer and it doesn't have the login lockout, so you just want to try all the possible passwords. And let's say that the passwords are just of length 2, right? So how might you do it? Well, you might say, okay, so my alphabet. So for brevity's sake, I'll say like the alphabet is A, B, C, D. And then you just say, okay, so for letter 1 in alpha, for letter 2 in alpha, so in this case, I'll just print letter 1 plus letter 2. I'll uncomment this. A lot. So this is what happens. It's exactly the same as before, right? So I'm saying for letter one in alpha, so letter one at first at A, then B, then C, then D. And then I'm saying for letter two in alpha. So when letter one is equal to A, I'm saying, okay, letter one is A, not paying attention to that, just running the inner loop. The inner loop just says for letter two in alpha. So letter two is A, then B, then C, then D. So that's why letter one is fixed. And this loop runs, and letter two is A, then B, then C, then D. And then you're done. So that means that, okay, this block has finished running. Go to the next iteration. Letter one now becomes B. So you go BA, BB, BC, BD. All right. Why is it combinations? Well, just because I printed letter one plus letter two. So this is like, first it's like A plus A, then it's A plus B, then it's A plus C, then it's A plus D. And then I'm done with the iteration. So it becomes B plus A, B plus B, and so on. Okay. So that is a way of listing every possible I with every possible J, every possible letter one with every possible letter two. You could do something like this. So what's happening now? So I'm saying for letter one in alpha, and then run this. So again, at first, the first time it happens, letter one is just A. So I'm saying letter one is A, that's fixed. Don't pay attention to that. And now run for letter two in alpha, for letter three in alpha. We already know what that does, right? So that makes it so that we have all the possible letter twos with all the possible letter threes. And then when we're printing, we're saying print letter one plus letter two plus letter three, right? So if you just look at that part, letter one is whatever it is, it's fixed. And then letter two and letter three change, and there are all the combinations. Make sense? And you could do it. So we'll see later on a little bit how to make it so that you don't have to type this out, because you can see how this becomes unsustainable. But you can have all the combinations of 4 letters. Right? So, oh, lead code, no, not lead code medium. So lead code medium is like the more difficult questions on ESC180. So by medium, I didn't mean anything with medium. So like the best way to gauge kind of the midterm is to just go to the course webpage and look at past midterms, which are all here. So you can just take a look. Lead code easy. To be honest, I don't have like a very good idea what lead code easy is, so I don't know. But like if your question is literally, am I passing ESC180? The answer is yes, you probably want more than to pass. But yes, if you're doing lead code easy, then you're fine in terms of passing. I just don't have like a very good idea of what lead code easy is, so I can't say kind of how it is compared to the midterm, but you can look at the actual midterms and you'll have an exact, well, a very accurate idea of what the range of possibilities is. So yeah. So in fact, so let's look at the midterm now, I guess. So obviously kind of the questions are different every year, but I'll just kind of go through the questions. I'll mark out which ones might be covered, which ones might not be covered. And I'll also kind of give you ideas about what those things are like. So write a function that takes a number n and returns a list of all the perfect squares between 0 and n. So a perfect square is a number such that k squared is equal to s for some integer k. So that means that, for example, 4 is a perfect square, and then 9 is a perfect square, and then 16 is a perfect square, and so on. So this question, I think, right now, I think for most of you would not be that easy. I think after you do this week's lab, you'll see that it kind of resembles one of the questions on the lab. And that's an important component of it, right? So when I write the midterm, I kind of look at the questions in the lab and I say, what would be a reasonable problem to ask of someone who has solved the lab? So definitely you should know how to solve the lab problems from scratch. This one you haven't done yet. Yes. So you can look at the solutions, and there is a marking scheme, for example, for question 1. So like this. So, all right. So approximately how to do it. Actually, this is kind of reminiscent of the missing k solution that I just gave, in the sense that one thing that you can do is you can just go through the elements and say, is that a perfect square? Is that a perfect square? Is that a perfect square? And then if it is a perfect square, you add it to the resultant solution. Right? So so that's kind of like how you would do it. Yes. No, so we haven't covered time complexity on the exam. Once we have covered time complexity, you'll see some past questions that specify this has to be within this time complexity. By default, it would never be, like, if it runs, it's fine. By default, like if the question specifies it has to be this much, then so okay. So write the function that computes the product of the element of a list of integers. So for example, product 2, 3, 4 returns 24. So this is like one of the easier questions, although again, so you haven't yet done a lab that's about lists. So it shouldn't look like that easy to you, probably, for most people. So again, kind of the technique is you start out with some kind of result. So result 1 makes sense because you're going to multiply result by L at 0, then L at 1, then L at 2, and so on. So then you go through all the elements of L and you multiply results by E. And then you return result. So again, kind of, I think especially if you haven't programmed before and you're looking at it now, before doing this week's lab, it's gonna look kind of intimidating because you haven't yet done the lab about lists. So after this week, a lot of the questions should make more sense. It kind of has to be that it's kind of weighted heavily towards the recent stuff, just because like we started from scratch. So it wouldn't make sense to ask like a lot of questions about like material from week 1 or something. Okay, so that's like that. So the basic technique is you set the result initially to be whatever is like the basic answer. And then you go through the list and you update the answer as you go. In this case, by multiplying by element 0, element 1, element 2, and so on. So write the function with the signature duplicates list 0, which returns true if list 0 contains at least 2 adjacent elements with the same value. So this is related to an example that we've done where you had to have information about indices. So the basic idea is you need to check, is list 0 at I equal to list 0 at I plus 1? So that means that you have to go through all the i's. So you'd say for I in range length plus 0 minus 1. Minus 1 because you have a plus 1 here, so you don't want to go over. And then you ask, is this equal? And if it's equal, then there is a duplicate. If not, then you keep going. So the key idea here is you can go through a list using for I in range and then use like list 0 at I, rather than do something like for E and L. And you need to do that if you need some notion of neighboring elements. So this one is very similar. So there is no time to read it, but this one is basically repeating the idea of keeping track of state in a global variable the way you did in project 1. Question 4 should not make sense to you yet. We haven't covered it. Question 5, we probably will not cover. Question 6 is actually, I messed up a little bit and put 2 questions that had to do with a global variable. This is also similar to login in some ways, and similar to last week's lab where you had to do something with pi, although let me tell you, so like if you read it, like basically it needed like the next digit of pi, and some people actually like put in the digits of pi that they had memorized on the paper, and then it was a dilemma of how to grade the people who did that, like subverting the point of the question, but then they remembered the digits incorrectly, and that was several people. And then it's like, well, I mean, I would give you full marks if you subverted the question but got it right, but if you like pretended that you know the digits but you don't actually, then it's unclear what you did for the question. I don't remember what, like they did not get full marks, obviously. I do not remember how much we subtracted. Anyway, I'll see you Wednesday. Thank you.